Hello students, welcome to Sarasa classes. In continuation to the third lecture, we will be discussing today the stereoisomerism part in coordination complexes. And as I've said in the third lecture, that coordination complexes can be divided into structural isomerism and stereoisomerism. In the stereoisomerism, we will be covering geometrical isomerism and optical isomerism. So in the first part of the lecture, we will be discussing geometrical isomerism. So out here for the geometrical isomerism, we will take up the square planar complexes initially. So I'm discussing as in types, okay? So suppose if I say MA4, what do I mean? And whenever I say n plus minus 0, that means this particular square planar complex can be neutral, positive or negative, where the value of n can be 0 or it can be positive or it can be negative. That is what I mean out here. My M is the central metal ion. A is a monodentate ligand, and the ligand can be neutral or it can also be negative. Okay. So what is the type of arrangement that is possible geometrically? Idea is to place the ligands on the vertices of a square, and that is how we will be generating a square plane, as I am showing with the highlighter. And as I said, we will use a third bracket followed with n, which can be plus, minus or 0. Now this particular arrangement which I have shown over here, can there be any other arrangement indistinguishable? We will say no. Okay. Again, some further information. What are the angles between these AMA? It is all 90 degree. So they are lying in one particular plane. And what is called the plane? The plane is called the square planar plane. What can be the examples that we may have covered before, which is Cu NH3 whole 4 2 plus, PdCl4 2 minus, PtCl4 2 minus, NiCN4 2 minus, NiDMGH, which is dimethyl glyoxime. So we have already shown that there can be negative complexes, there can be positive complexes, there can also be neutral complexes. Okay. What other types can we have? M A2B2. Again, the same notation we are using for indicating the charge outside the complex, and we will keep maintaining it. So M for here, it is sure that it is a metal ion. A and B are not equal to each other. They are monodentate ligand. Let us write the M at the center of the square. Let us place the donor atoms at the vertices of the square. So what kind of arrangements are possible? We will say there are two types of arrangements that are possible, and that has been shown over here, in which the A and both B are having 90 degree angles in between each other, And in other case, they can also have an angle of 180 between each other. When they are having an angle of 90, we will be calling this as cis. When they are having an angle of 180, we will be calling this as a trans. So this is showing geometrical isomerism. We will say GI. A very beautiful example will be PT Cl2 NH3 whole twice, and this is, if it is cis, then it is called cisplatin. Okay, cisplatin is basically a drug used for anti-cancer treatments, or was used as an anti-cancer treatment drug. Now it has been replaced with carboplatin, etc. So the other one can be the transplatin. So whenever we say transplatin, the angles between the Cl, PTCl will be 180. Whenever we are saying cisplatin, the angle between Cl, PTCl will be 90 degree. Okay. What about the dipole moment of this kind of complexes? Out here we will say that since similar atoms are having an angle of 90 degrees, so this will be having a dipole moment that is not equal to 0. But out here we will say that here the individual moments are getting cancelled because the ligands are lying at 180 to each other. So over here the dipole moment should be equal to 0. Another type of complex, MAAB2, wherein AA is a bidentate ligand, B is monodentate ligand. They can be either neutral or they can be negative. Okay. Now, what type of geometrical arrangement is possible for this type of a ligand? We will say such bidentate ligands which we are representing by connecting the donor positions A via curved arrow, like I have shown over here, there is a curved arrow. So it can only take positions wherein the angle, this angle is 90. Okay, that is the important part. However, if you wanted the AMA angle to be 180, okay, that means something like that, then we will say because of angle strain. Bidentate ligands cannot form three-membered rings. All right. So that means if we talk about an example, we will say obviously say PTENCl2. This complex can be used as an example of this type of arrangement. Again, another one we have MAAB. AAA means over here a tridentate complex or tridentate ligand, sorry, and B out here is a monodentate ligand. An example of a tridentate ligand is what? Something like this. Okay. What type of geometrical arrangement is possible for such a ligand? We will say what? M. One position is taken by a Cl. Say these are my donor points which are indicated by the A. The curved arrow, the curve is indicating the link. Okay. So this type of arrangement is only possible for this type of a ligand. Okay. And no other arrangement is possible. What is in the example? We will say PT dien Cl. So this complex will not be able to show any type of geometrical isomerism. Okay, and only one arrangement is possible. So we will say no GI. Okay. What if we change or use a bidentate ligand but with different types of donor points? Say we take some type MAB whole twice, where A and B are connected via a chain. This is a unsymmetrical bidentate ligand. Okay, with two different donor atoms. So if you think about placing this bidentate ligand donor atoms on the vertices of a square, then we can achieve one arrangement of this kind. Okay. Or we can have another arrangement in which we will say that this arrangement is possible. Whenever we have an angle of 90° between AMA, following the previous MA2B2 type of complexes, we will say this one is cis and the next one is trans complex. Let us now talk about examples. So in the examples we can say PT GLY whole twice, where GLY is an unsymmetrical bidentate ligand, basically an amino acid glycinate, where we can see there are two types of donor points, one coming from the O, one coming from the N. And if one wishes to draw the complexes, then this is how it will look. So this arrangement we will call as the cis arrangement, and the other arrangement which we have shown by switching the donor points, which is of this type. So one side we keep it same and the other side we switch. This one will be called as trans. Okay. So that is how we have to think. Now, there can be another type which is going to be M, A, B, C, D. We will say that A is not equal to B, B not equal to C, C not equal to D. So here all the monorented ligands are different. Okay, and how many isomers are possible in such a case? How do we find out these things? So you keep the position of A as fixed, write B, C, D. Now all you got to do in the next step is keep the position of A as fixed and keep switching. Okay, so if C out here is trans to B, A, then you make B out here trans to A. Okay, in the next one, again you're keeping A position fixed. So C was trans to A, B was trans to A, but D wasn't, so now make D trans to A. And in either positions you can place C or B. So out here, following this method, you can say that three types of different isomers are possible for the complex A, B, C and D. The complex A, B, C, D. Okay. In most part of the square planar complexes, whenever we are dealing with square planar complexes, one thing has to be kept in mind that this square plane molecule, suppose I'm taking any one example, okay? So I'm taking this example, okay, in which all the donor atoms are different. You try to treat all these atoms as pure, including the central metal atom. Now, what can you think of is that this molecule can be having a square plane passing right through the centers of the spheres, okay, and dividing each sphere into equal half. Okay, so whenever we have a molecule which has a plane of symmetry, idea is whenever a molecule has plane of symmetry, no optical isomerism is possible for a molecule having I center of symmetry or plane of symmetry, which we call as sigma. So most of the square planar molecules should be optically inactive, but there is a special case. What is a special case? Can a square planar molecule be optically active? Yes, it can. When a square planar molecule can be optically active when the ligand itself is chiral. So a complex such as PT, Cl, Cl, O, if this center is your asymmetric center, okay, why it is an asymmetric center? Because it has four different atoms joined to it, then this particular square planar molecule will be optically active. Why it is optically active? Again I am saying because this particular carbon is chiral or it is asymmetric. Alright, I hope that explains The section relating to geometrical isomerism or optical isomerism in square planar complexes. Keep visiting Saraswati classes. We will deal with geometrical isomerism in octahedral complexes in the next section. Thank you for listening.